we'll be covering these things in this tutorial. So what is MPI? So simple programming to run, how to run an MPI. So running your application with MPI CH. So more advanced topics, and then the conclusion finally. So this is the Moore's law that everyone knows. The process speed is no longer double for every 84 to 1824 months, and we can use also they'll be using parallelism in this norm. So even USPS uses this, airline industries and automobile companies use this for car crash simulations, something like that. And then shared memory programming, I mean the threads model in the lock and unlock models, the transfer parallelization, I mean they'll be using on sequential programs, the directed based parallelism, which is an open MP, which we'll be discussing when we go through these slides, and then the message passing, I mean explicitly for communication, for sending and so the message passing model. This process is traditionally a program counter and address space. The process will be having multiple threads. The MPI is for communication among processes which are separate space addresses, and it consists of synchronization and moving of data from one address space to another address space. So here is an example for a message passing model. So here we are taking a sorting integers example. In the beginning there will be a simple one process, and then the later step will be dividing it into process 1 and process 2, and then we'll be sorting into one process. So this is an example of that. So what exactly is an MPI? So as I said before, MPI is a message passing interface which was organized in 1992 when with the vendors like IBM, Intel, TMC, and so many other things. So it finished in 18 months. It takes fixed arguments, it has fixed semantics. So what exactly is not an MPI? It's not a language or a complex specification. It basically is not.
So this is an MPI 1, which is the first version of an MPI. It consists of variants of so many process topologies, C, C++ and bindings, error ports and classes, and blocking sends and receives.
So MPI standards. I mean the second version of MPI was released in 2000. So it has several features containing threads, I mean remote access functionality, and the later versions 2.1 and 2.2 were released in 2008 and 2009 respectively, and the MPI 3 was released in 2012 with several new features added to the MPI. So
where is MPI used? So there are some applications where we use an MPI specifically. It's used in nuclear physics, photonics, high pressure fusions, geology, seismology, mechanical engineering, electrical engineering, computer science and mathematics.
So why is an MPI? I mean, the MPI is an only message passing library, which is considered the standard one. So it has replaced all previous message passing libraries. The portability. So we don't need to change the source code whenever if you just use a different platform. I mean the performance opportunities. I mean the optimization performance is very good in this MPI. Functionality, I mean it has various features, etc. features. The availability, I mean it is in public and private domain, so public and both vendors both can use this MPI. So MPI CH is a popular open source and free implementation of MPI. So this is a simple communication model, as you can see that the application needs to specify the okay. So there are three questions in here. So how do you compile an MPI application? How will data be described? How will the process be identified? So compiling and running MPI applications. So MPI is a library, as you know that the code can be written in C, C++ or Photon. The compilation, how do you compile these things? Particular, as you know, the GCC test.c means some geo and the application. But in MPI applications, it's different. We use MPI CC and then remaining the same for everything. Execution. I mean, in regular applications, we use / some application name. So here, so you'll be running with 16 processes. The MPI execution -np 16 dot the application name. So this is a simple MPI programming. So which have a different header MPI.h, which also have MPI init arguments, and then finally MPI finalize. So the data communication in MPI is like a email exchange. So sender has to know whom to send data, what kind of data should be sent, and the tag for a message. And the receiver should have to know who is sending the data, what kind of data is being received, and the tag of the message. So blocking. What exactly is a blocking? The message buffer is described by buffer count and data type. So target bus is described by text and communication. So tag, as I said before, tag is a user defined type for message.
So this is the MPI basic receive. So it waits until a message will be mapped so that a buffer can be used. So source is ranked in the communicator, and the count will be received upon a fewer data types. So there will be also a status which contains further information, how much data was actually received, who sent the message, which tag was used.
I mean, this is the simple communication with an MPI. This is a code which uses. The user sends the data and receives.
So this is a parallel sort using MPI send and receive. The rank 0 consists of unsorted integers, and in the later process, the rank 0 and rank 1 will be divided, which is the leftmost part is the rank 0 and the rightmost part is the rank 1. And then the final step will be getting a fully sorted integers. So this is a simple program about parallel sort using MPI send and receive.
So what exactly is an MPI? So MPI is a high performance widely implementation of MPI. There are so many MPI features: MPI 1, MPI 2.0, 2.1, 2.2, and 3.0, which I mentioned before. So the current release of MPI CH is 3.0.2. So this is a website where you can download MPI-CH. So how do you compile MPI programs with MPI-CH? First C programs, as I said before, MPI-CC test.c under underscore o, the application name. Running MPI programs with MPI-CH, as I said before. So we need 16 processes for the local node, MPI execution, n-np, 16 dot application name. So if there are many nodes, it might be easier to create a host file, underscore cat hf.
So this is how you debug the MPI programs. So first one, the parallel debugging is trickier than the debugging serial program. So MPI-CH provides stability for that, and it also natively interoperates with commercial parallel debuggers, TotalView and DDT. So you can use MPI-CH with TotalView, and you can also use MPI-CH with DDT on one process.
So blocking communication, as I said before, the MPI send does not return until buffer is empty, and the receive does not return until buffer is full. So the process of sending data will be blocked until the buffer is empty. The process of receiving data will be blocked until the buffer is filled. This is the send receive diagram. So non-blocking communication. The non-blocking asynchronous operations return until the request handles can be waited for and queried. So non-blocking operations allow overlapping communication and computation. The combination of blocking and non-blocking senders can also be used to synchronize execution and instead of barriers.
So this is a basic non-blocking send receive diagram which you can see.
Hello everyone, my name is Satish Reddy. I'll be taking over the presentation from here on. So let's see the slide: message completion and buffering. So let's see the points for a successful communication. Initially, the sender must specify a valid destination rank to where it is exactly going. At the same time, even the receiver must specify the valid source rank from where it's receiving. The communicators must be same, tags must definitely match. Also, the receiver's buffer should be large enough to accommodate. Well, when the user's supplied buffer can be reused, that's when the send has actually completed. So that's a point to be noted. And then there's another point as well. It's like if a send is completed, it doesn't always mean that even the receiver has completed, because you never know what exactly happens in between the communication process. And for the main reason for this could be the message. It may be still being buffered in the system, or it may be still in the transit, so we never know. Here is an example for non-blocking communication. You can see the blocking communication on the top and the non-blocking communication in the bottom. Here is a simple programming example for non-blocking communication using if-else loop. Deadlocks. All of the sends may be blocked so as to wait for a matching receive. Also, they wait for like large messages as well. The variation of sequentializers are explained only except for the bottom press blocks. Defer synchronization. Basically, send and receive accomplishes mainly two things. One is data transfer and the other is synchronization. In most of the cases, there is more than the required synchronization. Using non-blocking operations and MPI wait all, we can defer the synchronization. There are also tools that can help out with identifying the performances issues. Like MPI is a profiling library, so that comes with the MPI CH implementation of MPI for understanding performance data. Also, the jumpshot tool uses MP datasets to show performances problems graphically. Introduction to collective operations in MPI. Collective operations are called by all processes in a communicator. MPI underscore bcast distributes data from one process to all the others in the communicator. MPI underscore reduce it can be used to combine data from all processes in the communicator and then it returns to one specific process. Also, in many numerical algorithms, SEN or RECV can be replaced by bcast or reduce, which gradually improves the simplicity and the efficiency as well. MPI collective communication. Communication and computation is generally coordinated in between a group of processes in a communicator. Tags are not used, which means different communicators deliver same functionality. There's also non-blocking collective operations in MPI3, which is basically covered in the advanced tutorial. Also, there are three classes of operations: one, synchronization; two, data movement; and three, collective computation. Synchronization. MPI underscore barrier. It generally blocks until all the processes in the group of the communicator calls it. One specific process cannot get out of the barrier until all the other processes have reached the barrier. Collective data movement. Here is a simple pictorial representation where there are two pictures, and the first picture is representing the broadcast, and the second picture you can see the scatter as well as the gather. More of the collective data movement. Here you can see how all gather looks like in the first picture, whereas you can see how all to all works in the second picture. Collective computation. In the first picture you can see how P0, P1, P2 and P3 are reduced and gathered into a single cell, whereas in the second picture you can see how scan works and each cell grows cumulatively and then adds up the previous elements. MPI collective routines. Here are a few of the routines: MPI underscore all gather, MPI underscore all gather V, MPI underscore all reduce, MPI underscore all total, MPI underscore all total V, MPI underscore bcast, MPI underscore gather, MPI underscore gather V, MPI underscore reduce, MPI underscore reduce scatter, MPI underscore scan, MPI underscore scatter, and MPI underscore scatter V. Here, in the previously stated routines, all versions generally deliver results to all of the participating processes, whereas V are the versions that only allow the hunks to have different sizes. Also, MPI underscore all radius, MPI underscore radius, MPI underscore radius scatter, and MPI underscore scan. These four routines are different from the others in such a way that they can take different functions, like both the built-in functions as well as the user-defined functions. MPI built-in collective computation operations. There are a few operations which are listed on the screen. As you can see, MPI underscore max, which represents maximum, MPI underscore min, which represents minimum. In the same way, prod, which is product, sum, which is sum addition, land, which is logical, which is basically like L and LOR, which is like L or, which is logical or, LXOR, which is logical exclusive or, band, which is bitwise, and then BOR, which is bitwise or. Then there's BXOR, which is bitwise exclusive or. Also there's max LOC, which is my maximum end location, and also there's minimum LOC, which is like min LOC, which is minimum end location. Defining your own collective operations. We can actually create our own collective computations using MPI underscore op underscore create, also MPI underscore OP underscore free, user underscore FN with the parameters. So the user function should generally perform inout vec of I equal to inout in vec of I OP inout vec of I. So from I to 0. The user function, it has to be associative, but it also can be non-cumulative. Calculating pi. Calculating pi using numerical integration. First we have to divide interval up to subintervals, and then you have to assign those subintervals to the processes. Each process will then calculate the partial sum. Once we have the partial sum, we can add all those partial sums together to get the value of the pi. Below are the parameters. So W is the width of each segment, which should be 1 by n. Distance, which is d of I, of course of segment I. From the origin will be I into W. The height of the segment I, it should be the square root of 1 minus d of I whole square. Here is a programming example to have the value of pi in C language. Introduction to data types in MPI. Data types generally allow to deserialize the arbitrary data layouts into a specific message stream. As we know, the networks generally provide serial channels, which is same for both the block devices and the input-output as well. Several constructors allows the arbitrary layouts, where the recursive specification is definitely possible. Declarative specification of data layout, what and not how leaves optimization to implementation, which are basically one of the many unexplored possibilities. Also, choosing the right constructors is not that simple. Here is an example of the derived data type. MPI's intrinsic data types. Why intrinsic data types? The main reason is heterogeneity, which is it makes easier for us to send it from C language to Fortran. Also, the conversion rules are complex, and length matches to the language types, so that you don't have to always declare the size. Users should generally use intrinsic data types as a basic data types for communication and type construction. So therefore, MPI underscore byte should be avoided at all cost. MPI 2.2 has added some missing C types, for example, unsigned long long. MPI underscore type underscore indexed. This helps in pulling irregular subsets of data from a single array. It has dynamic codes with index lists, and of course, it is very expensive. MPI underscore type underscore create underscore indexed underscore block. It is exactly like create underscore indexed, but the block length is the same. MPI underscore type underscore create underscore h indexed. It is indexed with non-unit displacements, for example, pulling types out of different arrays. MPI underscore type underscore create underscore struct. It is the most general constructor which allows different types and arbitrary arrays. Also, it is expensive. MPI underscore type underscore create underscore subarray. It specifies subarray of n-dimensional array of sizes by start of starts and size of subsize. MPI underscore type underscore create underscore D array. It creates distributed array that supports block, cyclic, and node distribution for each dimension. Also, it is very useful for input and output. Let's get to the conclusion now. Parallelism is very critical today, as this is the only way to achieve the performance improvement with a modern hardware technique. MPI is generally an industry standard model for parallel programming. A large number of implementations of MPI exist in both public domain and the commercial spaces as well. Virtually every system in the world uses MPI. It gives users the exploit to control on data management. It is being widely used by many scientific applications with great success rate. Thank you.